So for the rest of this series of lectures, we're going to focus on a specific kind of relation called an equivalence relation. Right, and that is a relation that has all three of these properties that we've been talking about. It's reflexive, it's symmetric, and it's transitive. When you have a relation like this, it creates these things called equivalence classes. Right? The way we define an equivalence class is if you take any element out of the set the relation is based on. The equivalence class of A, written like this, is just the set of all elements that A is related to. Right? So I've got that defined here, right, using this set notation. The equivalence class of A is the set of all x's in A such that x and A are related to each other. Okay, kind of abstract definition, right? Let's look at some examples and see what we're talking about here. So I have a relation here. We've actually talked about this one a little bit before. It's this equality relation. But what I want you to really notice here is we're only going to talk about rational numbers here, not all real numbers. So first, I know we talked about the equality relation before, and I believe we did actually show that this is an equivalence relation. If you haven't watched that previous lecture, you're welcome to go and work through that on your own. It'd be a good exercise. But what I want to talk about specifically here is what are the equivalence classes of this relation? And to do that, well, let's look at some specific examples. Let's say we look at 1/2. Right? What are the equivalence classes of 1/2? Well, it's every fraction, every ratio of two integers that's equal to 1/2. So obviously 1/2 is equal to itself, right? But there are others, right? 2/4 is a rational number, and it's also equal to 1/2. So is 3/6 and 4/8, and so on. There's actually more than just one number, than the obvious one number, in 1/2's equivalence class. Now let's try one more here. How about if I did this with 4? Well, obviously 4 is equal to itself, but 8/2 is equal to 4. 12/3 is equal to 4. 16/4 is equal to 4, and so on. Again, it's not just the original number, right? There are lots of numbers, lots of rational numbers that are equivalent to this one. In fact, if you flash all the way back, right to, I don't know, 3rd or 4th grade when you're first learning about fractions, that really was the point of reducing or simplifying a fraction. You had these two fractions that represented the same amount, and you wanted to reduce it down to just kind of its simplest form. Okay, so how could we generalize this? Well, if I take an arbitrary rational number, right, its equivalence class is the set of all rational numbers such that x is equal to n times p over n times q for every integer n. Right? Take p and q, multiply them by any integer you like, and you will get a number that is equal to the original fraction, just by reducing, right, canceling out those two n's. Right, so there's one example of how we can define equivalence classes given a specific relation. So I've got another relation here for us to take a look at. This time we're going to deal with the integers, right, not the rational numbers, and we're going to think in terms of this modularity, right? I'm going to define two numbers to be related if they are congruent to each other modulo 4. Remember what that means, right? I know usually when we talk about congruences, I usually like to go to the equivalent definition, right? I would say two numbers are congruent if their difference is divisible by 4. But here, I think it actually is helpful for us to stick to the remainder definition. Right, x is congruent to y mod 4 if x and y have the same remainder when divided by 4. All right, so with that in mind, I want to think about what the equivalence classes are here. And this would be a good case where you can pause the presentation if you like. All right, try to work these out on your own. Then jump back in and we'll do it together. All right, so we're going to kind of follow a similar approach, right? Let's just start with the number, right? What's the equivalence class of 0? All right, well, obviously 0 is equivalent to itself. Right, 0 and 0, they have the same remainder when divided by 4. And that remainder is 0, by the way. Right, so I need other numbers whose remainder is 0 when I divide them by 4. Well, the numbers that have that property, they're the multiples of 4. Right, so I would say 4, 8, 12, and so on going up. And the negatives work as well, right? -4, -8, and down. Right, so every multiple of 4, positive and negative, would be in the equivalence class of 0. All right, so let's go up a level. And let's just take the next number. What's the equivalence class of 1? Well, again, obviously 1 is equivalent to itself. And the remainder when 1 is divided by 4 is 1. So essentially, I'm looking here for all the numbers that have that same remainder. So I'm thinking 5, 9, 13, and so on. And you need to be a little careful when you do the negatives. Every time I do this, I want to say, okay, -1, -5. No, not how it works, right? -3, -7, and so on. Now, when you're going on the negative side, I mean, you can try doing the long division if you like. When you go to the negative side, this is the side where I think it is easier to think about that divisibility definition, right? The difference of 1 and -3 is -4, and -4 is divisible by 4. Therefore, the two are congruent. -7 minus 1 is -8. -8 is divisible by 4, so those two are congruent, right? I think it's a little clearer if you try using that definition with the negatives. All right, so let's keep going here. Right? If we do this with 2, you should get 2, 6, 10, 14. Those all have a remainder of 2 when divided by 4. And again, when we go to the negatives, got to be a little careful. -2, -6, and so on. -2 minus 2 is -4. Good. -6 minus 2 is -8. Good. Those are both divisible by 4. Right? You can see the pattern developing. All right, so let's do one more here. We should actually be done. So let's do the 3s. 3, so where are we going? 3, 7, 11, 15. And going down here, what do we get? We get -1, -5, and so on. And that's it. Right, those are all of the unique equivalence classes. And to see why, try doing this with another number. Right, try doing this with 4. For example, we'll notice 4 is already in an equivalence class. Right, so 4 I already know is equivalent to 0 and 8 and -4 and 12 and so on. This set is going to be the same as that one up there. And the same thing would happen if I try to do this with 5. 5 is already in an equivalence class. So 5 is going to be equivalent to 1, 9, -3, 13, and so on. And what I really want you to notice, two things, because it's going to be important in the next lecture. First, I want you to notice that these 4 classes here, first, that they're mutually disjoint. No two of them have anything in common. And second, I want you to notice that if we put them all together, we get the set A. Right? I've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, so on. And we get the negatives, -1, -2, -3, -4, and so on. Right? So what I'm seeing here is that these 4 equivalence class, these 4 equivalence classes are actually a partition of the original set A. All right, so that's what we're going to talk about in the next lecture. In the next lecture, we're going to show that not only does a partition induce a relation, but a relation, if it's an equivalence relation, right? It's not 100% reversible, right? An equivalence relation is also going to induce a partition.